Okay.
Go ahead.
Thank you, Turkey, for the introduction. I also thank myself for the invitation. It's very good to talk here. In the abstract, I said some things about Boğaziçi University students and academics. I wanted to say a couple of things about this. Then I thought I'm too old to do this. I graduated from Boğaziçi about 8 years ago. So I wanted some Boğaziçi students to come and talk because they have been protesting about this new appointed rector by the president for more than over a month now. And they have been called names. They have been said be terrorists and stuff like this. So I was in contact with one of the students from Boğaziçi math department. They wanted to write something and they wanted to give a message about this protests and everything. I invited them here, but this morning I received the following message. We have finals now and we are trying to solve math problems. I will not be able to make it. So these are terrorists, according to our president of Turkey, but they are trying to solve math problems and too busy protesting and solving math problems. They will not be able to give their message now here. So that's it. That's the message. They write their final exam at the moment. All right. So today I will talk about annihilation of cohomology over curved singularities. This was my thesis topic. And it's been a while since I talked about this. And I wanted to talk about this because I wanted to be very accessible. You will see in the first slide that it starts very accessible because I thought there will be a lot of undergrads here. Let's go. Okay, so starts from elementary school. You know that the product of two non-zero numbers cannot be zero. So if you have two numbers and if the product is zero, then one of them has to be zero. But then you go to, I guess, high school or university, and you take a linear algebra course and you see that this doesn't hold in matrices. The product of two non-zero matrices might be zero. And you can say the same thing in terms of linear transformations. The composition of two non-zero linear maps may be zero again. And this happens in the space of matrices if the column space of one matrix is inside the null space of the other matrix. In terms of functions, this means that the image of one map is inside the kernel of the other map. Okay, then a reasonable question to ask is, what can you say about the image of G and kernel of F? How can you compare them? Are they equal? Maybe they are equal. So this image of G inside kernel of F just means that if you hit something with G, or if you send something with G, F will take that to zero. F might take other things to zero, which is not in the image of G. Or it might be the case that only elements that F takes to zero are the things which come from G, right? And you want to compare these things. Now, maybe an algebra course now in the third year of undergraduate curriculum. You have a ring. A chain complex of modules is something, an object that consists of modules and linear maps. And they are, let's say, on a number line. You know, they are linearly oriented like this, such that the composition of two consecutive maps is zero. So what we had in the first slide happens here. The image of di plus 1 is contained in the kernel of di. And these are important objects. And we measure the, whatever I called in the first slide, the ith homology. We measure how much the image of di plus 1 is different than kernel of di by these homology groups. And that's the quotient of kernel of di by the image of di plus 1. If the kernel of di is equal to image of di plus 1, then hi is 0. If not, hi is not 0, and it might be complicated depending on what complex we are looking at. Okay, so now I have a ring R and two finitely generated modules M and N. A free resolution of M is a chain complex of free modules. I will denote this by F. Now, in the previous slide, it was going up until infinity on both sides. On this one, I stopped at 0. It just means that it will continue to be 0, 0, 0, 0, 0, 0 on the right-hand side. On the left-hand side, it can go to infinity possibly. And we have these free modules such that the homology at each of these i's for every positive I is 0, and the 0th homology is M. If you look at this carefully, H0F is the image of D0 modulo the kernel of D0 modulo the image of D1. D0 is the 0 map, as you can see. So the kernel is everything. Then you look at F0 mod, the image of D1. That's the co-kernel of D1, if you know what it means. Now, when you have a situation like this, you can cook up a new complex. And this complex has as modules the set of R linear maps from these free modules Fi's to N. That was our second finitely generated R module. And I put these maps deltas, and I define them as delta I of G is equal to G composed with Di. Let's look at this for, let's say, D1. So D1 takes an element of F1 to F0. And delta 1 should take an element of hom R F0n to hom R F1n. So it should take a function G that goes from F0 to N to a function from F1 to N. And how do I define this new function from F1 to N? Well, you take an element from F1, you first send it to F0 by D1, and then you apply G, and you are in F0 now, so G is defined. Anyways, nice thing about this construction is that you still have the consecutive maps composed to 0, but we might have homology now. So before, all the kernels were equal to images for positive I. But when we do this construction, we might lose that. So we might have homology. And we define X modules as this homology. So the xi of n by m, xi r mn, this thing that appears here, is equal to the quotient of kernel of delta I plus 1 by the image of delta I. All right, so it measures if when we do this home construction, we lose the fact that kernel is equal to image. If we don't lose it, then this xi is 0. If we lose it at some point, it is not 0. All right. So one thing about this is that we always have free resolutions of modules. It's not too difficult to compute or construct, but I don't want to talk about it too much. I'm already running a little bit behind. Yeah, so we can always construct this. Okay, I think that's enough. Now, what's our problem? I want to describe what I'm going to be interested in. That was a gentle course in homological algebra. At the end of 19th century, Hilbert proved that if you have a polynomial ring, then if you pick any two modules Mn over this polynomial ring, let's say a polynomial ring has d variables, then xd plus 1 is always 0. That's a very fancy way to talk about Hilbert's syzygy theorem. There are nicer ways to say what it is, but this is Hilbert's syzygy theorem for us now, because that's how I started the talk. And then later in the 20th century, we had a lot of people that contributed to this: Zariski, Serre, Austander, Buchsbaum, and more people. Let's say if we have a commutative Noetherian ring, and let's say this defines a smooth geometric object, spec R, then if the Krull dimension of this ring is D, then for any Mn, we have xd plus 1 is 0. Same thing that happens in polynomial ring happens in this case. If you heard the term global dimension, this just says that if you have finite global dimension, let's say your global dimension is D, then you will have this x vanishing after D plus 1. After D, I guess, starting from D plus 1. On the other hand, if you have infinite global dimension, you have for each I a pair of modules where this xi doesn't vanish. All right, so this happens when you are not smooth anymore, when there are singularities around. So the reasonable question to ask is, you have a commutative Noetherian ring, describe this ideal, Ca, stands for cohomology annihilator. It consists of all ring elements which annihilate these large xi's for all pairs of modules. And I want I to be sufficiently large. Since I choose my ring to be Noetherian, for I sufficiently large, this ideal is going to stabilize. Let me say it that way. All right, so that's the ideal that I'm going to talk about. I studied in my thesis, and I like it. It's a nice ideal. All right. And here's my motivation about the problem that I will be describing in a second. Suppose that you have the polynomial ring modulo one polynomial. Let's say this is x cubed plus y to the power 5. I'm not going to tell you how I computed this, but the cohomology annihilator ideal is generated by 3 elements, x squared, xy, and y cubed. There is also another ideal that's important when you have a hypersurface like this. It's the Jacobian ideal, and it's generated by the partial derivatives of this polynomial. And with respect to x, I have x squared, and with respect to y, I have y to the power 4. Actually, this is supposed to be a complete ring, so I wanted to take power series, but let's act like that's not an issue. If you look at the Jacobian algebra, which is the quotient of our ring by this Jacobian ideal, it's an 8-dimensional vector space. In the quotient, you kill x squared and y to the power 4. So in degree 1, you have 1. It's 1-dimensional. Degree 0, you have 1. It's 1-dimensional. In degree 1, you have x and y. But in degree 2, you have only x, y, and y squared because you kill x squared. And then since you killed x squared, you killed x squared y, or x cubed, things like this. So you have this nice shape. You always have this diamond sort of shape for the Jacobian algebra if you are an isolated singularity. That's a cool fact, but we don't need it. If you do the same thing with the quotient algebra by the cohomology annihilator, you only get half of it. You now kill xy and y cube as well. So you see you get only half of this left-hand side picture. And the thing is that my advisor computed a little bit of these examples and observed that this happens in every example. The dimension of the vector space on the left-hand side is always twice the dimension of the vector space on the right-hand side. And we were talking and he said, why is this happening? And I said, I don't know, but I needed to get a PhD thesis at some point because I was going into my third year. I said, you know what, let me just think about this a little bit more. Okay. Now we will do something that looks completely different. Coin problem, or chicken McNugget problem in popular culture, I guess. Here's a question that our non-existing undergrads can answer or try to answer. Which numbers can you write as 3a plus 5b, where a and b are non-negative integers? So we all know that if we allow a and b to be all integers, 3a plus 5b will be a set of all numbers that we can write as this is going to be an entire set of integers. That's called the Euclidean algorithm, or whatever. Ancient Greeks knew this. Here we restrict ourselves to non-negative integers only. And you have, let's say 0, you can write it like this. You can choose a, b to be 0. You cannot write 1 like this, because if you have one of a, b non-zero, you will get at least 3, right? So you can't write 2 either, but you can get 3. You can't write 4 like this, but you can get 5 and 6. You can't get 7, but you can get 8. And it continues like this. If you actually write your numbers in 3 columns like this, 0, 1, 2, 3, 4, 5, 6, 7, 8, it's very easy to see what happens. Since you get 0, you can keep adding 3 to it. So you get 3, 6, 9. So if you get a number in this column, you're going to get everything below that just by adding 3 to it. And that corresponds to choosing a to be plus 1. In the second column, we have 1, 4, 7, but we can write 10 as 2 times 5. And that's good. If we get 10, then we get everything below 10. 10 is 5 times 2. 13 is 3 plus 5 times 2. And in this last column, we have 2 that we cannot write, but we can write 5 as 1 times 5. And therefore, we can get everything below that. 5, 8, 11, and so on. On the other hand, if you write your numbers differently, you see that if 2 numbers add up to 7, exactly one of them is red. There are 8 numbers here until we reach our threshold, until the last element that we cannot write, and exactly 4 of them are red for this reason. And this is not this has some geometric picture too attached to this, but let's just focus on this coin problem. We have these 2 pictures. One of them was the quotient of our ring by cohomology annihilator ideal and the Jacobian ideal, respectively. And on the right-hand side, we have this coin problem, which numbers you can write as 3a plus 5b. And the theorem that I will prove today, well, I proved in my thesis, is that this is not a coincidence. So there's a reason that we have these 2 pictures. And 8 is equal to 4 times 2 in both of them. Okay, so that's kind of part 1 of the talk. Now we are going to do some more technical things. I hope it will not be too overwhelming, but I'm warning, it's not going to be this simple. All right, so the things that I like to do in math are all about maximal cohomology modules over Gorenstein rings. So the ring that we were interested in, the polynomial algebra divided by x cubed plus y5, or it's isomorphic to the subring of polynomial ring with 1 variable generated by t cube and t5. These are examples of Gorenstein rings. I'm not going to give you definition of what a Gorenstein ring is, but examples include regular rings. So these are coordinate rings of smooth algebraic varieties. You might be looking at the zero set of a single polynomial. So you have hypersurface rings. You might have more than one polynomial, but you might them to be nice, complete intersection rings, if you know what a regular sequence is. These are cut out by regular sequences. If you're interested in group representations, you have group algebras, or more generally, more self-injective algebras. And this can be non-commutative as well. We have a non-commutative notion of Gorenstein rings as well. Or there's this long adjective, cohomology rings of smooth, orientable, connected, compact manifolds. And if you remember what these adjectives, does anybody remember what these adjectives tell you? Where do you see these adjectives? I can't see the chat, so somebody needs to. I can see now. Nothing. Okay. If you have these adjectives, then what you have is Poincare duality in topology, right? When you have a smooth, orientable, connected, compact manifold, then you have a Poincare duality. And Gorenstein rings are sort of rings which also admit a nice duality, which in this, when we restrict to the cohomology rings of these manifolds, is Poincare duality itself. So these are rings which have nice duality properties in some abstract levels, and they are cool. The reason I want to study Gorenstein rings is that over these rings, there is a special class of modules called maximal Cohen-Macaulay modules. And these are modules with this ext vanishing property. So extensions of R by M is 0 for all positive I. And that's the defining property of them. Over non-Gorenstein rings, you can still define maximal Cohen-Macaulay modules, but there's actually a more nice way to define it. This is a homological description, which is an equivalent description only in Gorenstein case. But since I started with definition of X, I wanted to give this description. What does this mean? So you have a free representation, free resolution of M, and you do this home construction. Now you have another chain complex, and we said, okay, we might have some homology now. We are looking at things which do not have that homology. All right, so that's cool. Now examples include projective modules, or if you don't know what it means, we will always be interested in local rings later. So free modules. And if you have finite global dimensions, or if you're in the smooth case, this is it. You don't have any other maximal Cohen-Macaulay modules, so it doesn't give you anything. That's cool. And in general, if you have a ring of Krull dimension D, then these syzygies of modules, if you know what this means, are maximal Cohen-Macaulay. And over Gorenstein rings, actually every maximal Cohen-Macaulay module is a high syzygy, the syzygy of something. Okay, so these are maximal Cohen-Macaulay modules over Gorenstein rings. If you do not like the language of modules, and if you're a geometric person, remember Serre proved in 50s, FAC, Faisceau algebraique cohérent, in French, I guess. He proved that if you have a ring R, the category of modules over R is equivalent to the category of coherent sheaves on spec R. So if you like sheaves better than modules, you can just think about sheaves and not modules. All right, so here's a definition. Suppose we have a Gorenstein ring and two maximal Cohen-Macaulay modules. This is what MCM means. look at this set of phantom maps. So PMN is the set of all phantom maps. These are all R linear maps, which factor through a free module. So you say that F factors through a free module if there are these maps B, beta, and alpha, alpha from M to a free module F, and beta from that free module to N, which compose to F. So you can sort of factorize F into two maps, and these two maps are to and from a free module. Now I see that calling it F and calling my free module also F is not a good idea. And the definition that I want to do is the stable category of maximal common modules, which is this underlined MCMR, has the same objects as MCMR. So the objects are maximal common modules. These are what I'm interested in. But home sets are replaced by these new homes. You don't want to count the maps which factor through a free module. Now, it looks like a construction that came out of nowhere, but what you want to do is to identify free modules by zero. So let's look at this a little bit closely. If you have a free module, let's say F, and if you want to look at, if you replace M with a free module F, then you can take that alpha to be the identity map and beta to be F itself, which means that every map from a free module to something else factors through a free module. That free module is itself. Not too complicated. You can take alpha to be identity. You can also do this in the second component. You can replace N with a free module. In this case, you can take beta to be identity and alpha to be your map, which tells me that every map to a free module factors through a free module. I'm saying something very tautological right now. Therefore, if either M or N is a free module, then this underlined home is zero, because every map is factoring through a free module. So PMN is the entire thing. The quotient is going to be zero. And what does that tell us? That tells us that if we have a free module in this category, it has only one map from and to every other object, and that's the zero map. And if you know a little bit about category theory, that means that you are identifying free modules with the zero objects without S, zero object. Okay, that's the idea of this construction. And why did we do this? Because previously I told you that if you have a smooth, or if you have a coordinate ring, let's say of a smooth ring, if you have finite global dimension, then every maximal common module is free. So if R has finite global dimension, this category, stable category of maximal common modules, has only one element. It's just zero. It's trivial. So this category sort of measures if you have singularities or not. If you have a singularity, it's going to be a more complicated category. There's going to be non-zero elements. If there are no singularities, then it's trivial. So there is a reason that you want to consider this category. Okay, so now an introduction to derived categories in one slide. We say that two chain complexes are quasi-isomorphic if they have the same homology. You might have different modules, but the quotients of kernels via images might be the same. And by same here, I mean up to something, isomorphic or blah, blah, blah. Now, the bounded derived category of R is the category whose objects are all complexes of R modules, which are quasi-isomorphic to a bounded complex. That's what this little b means, bounded. And I do not want to tell you what maps are, what morphisms are in this category, because we don't need to. But the reason that you define those morphisms as what they are is because you want to identify two complexes if they have if they are quasi-isomorphic, if they have the same homology. And there's a way to do this, and you can nicely define home sets, and this becomes a nice triangulated category and such. But the idea is that you want to say two complexes are the same in this category if they have the same homology. So that's what you want to care about. Now, the singularity category is the quotient of this bounded derived category by the subcategory of complexes which are quasi-isomorphic to a bounded complex of finitely generated projective modules, not all modules which are quasi-isomorphic to, not all complexes which are quasi-isomorphic to a bounded complex, but the ones which are quasi-isomorphic to a bounded complex of projective modules or free modules, if you wish. If you have finite global dimension, every complex has a finite free resolution. Therefore, this subcategory that I'm describing here is sort of everything. If you have infinite global dimension, then there are some complexes which have infinite free resolutions, whose minimal resolutions are infinite. Therefore, again, this category measures singularities somehow. Hence the name, the singularity category. Okay. Now we have seen two categories which measure singularities, and they're actually equivalent to each other. So Ragnar Buchweitz in the 80s proved that if you have a Gorenstein ring, then you have an equivalence of stable category of maximum common quality modules with the singularity category. And this is cool because these maximum common quality modules now carry geometric importance. The left-hand side is also a triangulated category, and the right-hand side is a triangulated category. And this equivalence is an equivalence of triangulated categories, if you know what that means. So here's a small thing. You can take a module and you can identify it with a complex like this. So this complex has zeros everywhere except the 0th position. And at 0th position, you have your module M. And every map in this complex is just the 0 map. You can sort of embed your modules inside the derived category. Then you can look at its image in this quotient, in this singularity category. And then on the left-hand side, you have a corresponding maximal common quality module. And we say that this is the MCM approximation of your module. So this MST is going to be MCM approximation of some module M. It's an MCM module, and it lives in the left-hand side. So with this way, for every module, you have a maximal common quality module corresponding to it. It's going to be useful. All right. I said a module M can be identified with a complex. It's important that we do this in degree 0. So we have these modules, and in the 0 part, you have M, and every other thing is 0. You can shift your modules. You can shift these complexes to the left, to the right if you want. And then you are not concentrated in degree 0 anymore. M lives in some other degree, in some other cohomological degree. Now the fact is that in one of the uses of derived category is that these X modules are, or these X groups are home sets inside the derived category. So if you have two modules, M and N, this Xi that I described at the beginning is isomorphic to the home between M and N shifted by I inside the derived category. So I identified N with a complex, and I then shifted complex by I, and I get a new complex. Now, in the derived category, I look at the homes, the linear maps from M to the shifted complex of N. I didn't tell you what the morphisms are, but this is the morphism set. So this is one of the uses of derived category. And similar to this, you can do the same thing in the singularity category. You have your modules and you identify them with complexes, and you can shift these complexes to the left. And in the singularity category, you can still look at the home set. And in this case, we make this new definition. This is the stable X. And I just put an underline. So X is the home set in the derived category, and stable X is the home set in the singularity category. And the stable X of any two modules M and N is the same as the stable X of their MCM approximations. This is sort of by definition, right? Because M and M corresponds to MST, the MCM approximation inside the singularity category. So of course they have the same home sets. But we have this equivalence of Buchweitz that singularity category is equivalent to the stable category of MCM modules. And therefore, I can do my computations inside the stable category. Now, I guess I should have put one more home sets there, because now I need to tell you a little bit too many things at once. And so the stable X, if you look at upstairs, it's the home set in the singularity category between stabilization of M, or approximation of M, an MCM approximation of N shifted by I. I said this equivalence of Buchweitz was an equivalence of triangulated categories. And on the level of derived category, you have this shift functor, which is an autoequivalence of this category, which turns this into a triangulated category, if you know what it means. On the level of MCM modules, we have the inverse of the syzygy, co-syzygy. So this omega I is the ith syzygy of MCM approximation of M. And that comes there because of Buchweitz's equivalence that replaces that N shifted by I. Point is that I can do my computations inside the stable category of MCM modules. And now here's a nice fact that if you have a commutative ring of Krull dimension D, commutative Gorenstein ring of Krull dimension D, then for I large enough, if I is larger than D, then these stable X are exactly the same as original X. They do not give you any information. So the only place where this actually matters is before D. Okay, so here's our lemma. I'm going back to our problem. Suppose that you have a commutative Gorenstein ring. Then remember the cohomology annihilator ideal was the ideal consisting of all ring elements, which annihilate all large X modules. The lemma says that instead of doing this, you can look at the stable endomorphism rings of maximal cohomological modules and their annihilators. So these are home sets from M to M itself inside the stable category. And you want to look at their annihilators. Here's a proof. We want to show that the cohomology annihilator, so the first orange thing is equal to the last orange thing. This is scary, so I enumerated them. The first line is just definition of the cohomology annihilator ideal. The second line is the last fact from the previous slide. These regular X's are the same as stable X's for large enough I. And then this is another fact from this previous slide, that you can do this by taking MCM approximations, and you won't lose, I think. But we are looking at all modules and all of their MCM approximations. So I can just say, which I did in the fourth line, that I am looking at the stable X between all MCM modules. And one nice thing about this is that if I can take syzygies, and we computed that again from the previous slide, this is equal to stable home between the ith syzygy of M and N. I'm looking at the annihilators of that. And omega, the syzygy, is an autoequivalence in the stable category of maximal cohomological modules. So, and I'm doing this for all M, therefore I can just get rid of that. And that's the previous, that's the sixth line. And then the seventh line is just saying that if you are killing every map from M to M, then you are killing every map from M to N as well. And that's because, I guess in fancy terms, the home between M and N is a module over this ring, stable endomorphism ring of M. If you kill that, you'll kill the module. Okay, so that's the proof for this lemma. It tells that I do not need to look at all pairs of modules and X modules between them and try to annihilate them. I can just take MCM modules and look at their endomorphism rings in the stable category and annihilate them. Okay, so back to the problem. That's the last part of the talk. Let's go back to the problem. We have a one-dimensional commutative ring R, let's say. QR is the total quotient ring of it. This is just like the construction of rational numbers from integers. You may have some zero divisors, but what you do is you invert all the elements that you can invert. So all non-zero divisors will be inverted. By R bar, let's denote the integral closure of R inside QR. So these are just, this consists of all ring elements, or all elements in QR, which are solutions to a polynomial with coefficients in R. And COR is the conductor ideal. This is a set of all ring elements. When you multiply with R bar elements, you fall inside R. So R is a subring of R bar. And this is the set of elements in R, so that when you multiply an element of R bar, you are going to get something in R. Okay, so these are the new players in our game. In our example, we have that R bar is the polynomial ring of one variable. And the conductor ideal is generated by T8, T9, and T10. And if you look at this, if you multiply this with T cubed, you are going to get T to the power 11, T to the power 12, T to the power 13, So this conductor ideal contains all powers of t after 8. And remember what we had in the coin problem, after 7, everything was in the semi-group we generated. Now here's a little nice fact that in dimension 1, we know that R bar is a maximal cohomological R module. So R is a subring of R bar. So R bar becomes an algebra over R, in particular a module over R, and some maximal cohomological module. Okay, so now some lemmas. We have that the cohomology annihilator ideal is contained in this ideal, the set of elements which annihilate the stable endomorphism ring of R bar. Why? Because cohomology annihilator ideal is the ideal of elements which annihilate the stable endomorphism ring of every maximal cohomological module. Of course, they annihilate stable endomorphism ring of the integral closure. Another lemma. We have that the conductor is actually equal to this sort of stable annihilator, which was on the right-hand side of the inequality in the previous lemma. So when you combine them, you see that the cohomology annihilator ideal is contained in the conductor ideal. And the crucial point here is, I think, another lemma part, and seeing these things in terms of maximum cohomological modules. The last two of these assumes that R bar is finitely generated as a module over R. This holds if conductor contains a non-zero divisor. It holds, for instance, when you have a reduced ring, a complete reduced ring. Then in the 90s, a student of Craig Hunicke, Sinju Wang, proved that with this assumption as a reduced complete Noetherian one-dimensional local ring, we also have the other part of the lemma, other inclusion in the corollary that we had earlier. So if you combine them, you get a theorem. If R is a one-dimensional reduced Gorenstein complete local ring, you have that the cohomology annihilator actually coincides with the conductor ideal. Now, we are getting closer to saying why the two pictures that we had, coin problem and the quotient algebra picture, is the same. Okay. Now here's a theorem of Milnor and Jung. I guess they didn't prove it together, but one of them proved a more general version. It's combining these vector space dimensions of the Jacobian algebra with the quotient of R by the conductor. So if you have an algebraic plane curve singularity, Milnor-Jung formula says that the dimension of the Jacobian algebra is almost twice the dimension of R mod conductor. You need to correct it maybe with the term like minus R plus 1. Here, R is the number of branches of the curve at the singular point. You might have different branches. But the examples that my advisor computed were all unibranch. So R was 1. So they cancel each other and you get what you wanted to get. And then the theorem that we proved in the previous slide says that R mod conductor is the same as R mod cohomology annihilator, because conductor is the same as cohomology annihilator. Therefore, you have the same numerical condition between these two, relation between these two things. And since R was 1 in the examples we computed, we are done. As a corollary, this was not a coincidence. It was a corollary of Milnor-Jung formula from geometry. And that finishes the problem that we started. Now I have a little bit more time, I guess. Let me say a couple things. I think Özhan was here. Let me see. Yes, so when we were talking about Ulrich bundles, or when we were talking last week about quivers, we always talked about finite type. You can also look at Ornstein rings, which have only finite domain maximal Cohn-Macaulay modules. Well, on the finite domain indecomposable maximal Cohn-Macaulay modules. And it turns out that all of these things are classified by ADE diagrams again. We have seen it in talks of Özgür in the first semester. We have seen it in talk by, I guess in the first talk of the series by Emine, and then last week by Emre Şen. We have seen these ADE diagrams appearing. And the example that we were running with, this generated by T cube and T5, or the polynomial ring modulo x cubed plus y to the power 5, is the E8 singularity in dimension 1. In higher dimensions, we have also other things. They're also classified by these ADE thinking diagrams. And it's cool, I think. And I can generalize this theorem from dimension 1, not this theorem, but the previous one. Well, something else. I can generalize something else to arbitrary dimensions, and I can compute other examples. Especially in finite type, there are cool examples to compute. And I still have some conjectures about these things. I can't prove theorems, but I can compute examples with different methods, and they all point out the same thing. But I think it's a good place to stop talking now, because I feel like I will not be able to stop.
So thank you, Özgür, very much for this very nice talk. Let's think all together.